So in the yesterday afternoon session, we have discussed the way we introduce material related to second law of thermodynamics. Specifically, if you recall, we introduce it using the Kelvin-Planck statement as our primary statement of the second law. Going forward, then we define a heat engine, a concept of a heat engine, and show that the Kelvin-Planck statement results into the conclusion that a 1T heat engine, that is one thermal reservoir heat engine, cannot exist. And then we show that a 2T heat engine is possible according to the Kelvin-Planck statement, with the engine rejecting heat to one of the two reservoirs. And we extend that argument to create the hierarchy of temperatures. And then we define a reversible process at that point, after all this is done, and then introduce the Carnot Theorem. And of course, once the reversible process is introduced, before the Carnot Theorem is talked about, we can always introduce in fact, we do introduce the reversible cycle once the reversible process is introduced. So the succession of topics then after this point goes as introduction of the Carnot Theorem, then description of the Carnot cycle, more formal discussion on development of the thermodynamic temperature scale, after which the Clausius inequality is introduced. And using the Clausius inequality, the property of entropy is then finally introduced to the students. So just the way the first law of thermodynamics was utilized to introduce the property of energy, and more specifically thermal energy, if you wish, the zeroth law was used to introduce the property, thermodynamic property temperature. When it comes to Clausius inequality and the relevant discussion of it, the third important property, thermodynamic property, called the entropy, is introduced. So this succession, which I just talked about, is in the series of lectures starting with 20 to 32. And from Carnot Theorem onwards, all the way to the end of second law discussion, including evaluation of entropy differences and so on, is in the lectures 24 to 32. So with this as an overall summary of how the second law material is developed in this set of lectures, we can open the discussion. Thank you. Maybe prior to that, in case either Professor Bhandarkar or Gaitonde want to add on to this, please, I will request them to do so.
No, not really. I think you outlined how it goes. So now, if the participants have any, statements to make about any doubts, or whether they have any kind of comments on how
actually, what I would like to do now is, now that we have spent almost 2 days, right? One thing that I would really like to hear from participants now is looking at how this sequence has been designed and delivered so far. Is there any specific point that they would like to bring forth here to us, wherein they can say that, okay, this is the way now I think I will want to restructure my course, the way I teach it. So that will be a very, very useful input for us, I think. So that's something that I think we would like to start hearing in this last day, in addition to, of course, any discussion that is required. Yeah, Dr. Anandan, you have a raised hand. Go ahead, please.
Thanks for the opportunity. Yes, sir. Actually, I have learned something unique way of handling this subject. So I will surely restructure my way of handling thermodynamics to the students. the way we have represented the laws, and then first work, and then first law of thermodynamics, and then zeroth law of thermodynamics, followed by second law of thermodynamics, and then Carnot Theorem, and so on and so forth. So this is very much useful to me, and of course the students will also be understanding it in a much better way. Thank you very much, sir. This restructuring is much useful.
Okay, that's good. Of course, what I will strongly recommend and suggest is before you get the opportunity to teach this the next time, whenever it is, I think it will be a good idea to go through this again in a very careful manner to see how students may end up appreciating this. And to do that, perhaps the best way is to start thinking ourselves as students and realize what is possibly the most clarifying thing about this sequence, and that's the way I think you'll be able to convey these ideas as clearly as possible to the students. I think this is the way I would like to at least suggest. And I also see a comment Miss Madhu, I think, has written. So with reference to that comment, again, something this I mentioned yesterday, using these lectures as a framework, if you wish, for running this thermodynamics course as a flipped mode, in a flipped mode. Of course, what ends up happening in a flipped mode is something that I should also sort of point out. If you assign a certain set of lectures to be viewed, let us say in week n, and in the n plus first week, all that you are going to be doing is discussion on the topics that were covered in those lectures in week number n, which the students have viewed. And it's more like a discussion session to try to clarify things, possibly work out a few problems as you clarify things. And so in some sense, at least I found that when I did this in a flipped mode, the preparation level that I needed was much higher, because there was no formal teaching to be done at all anymore. So there was no time assigned for teaching. That supposedly has already happened through the viewing of those lectures by students in the previous week on their own. And so those students who actually get interested, and believe me, there are many who do, once they go through this set of lectures, I have at least observed that there are a reasonable number of students who get interested, and then they start thinking a lot. And when they start thinking a lot, they bring a lot of questions in those discussion sessions and so on. And in order to address those questions in a most reasonable manner, one has to be quite prepared. And I think what helps in this is having a set of nice questions and problems at our disposal, so that you can intersperse the discussion with solving some of those problems, or at least posing those problems or questions and discussing those in the class and so on. And that's why the graded activity for this specific workshop we thought should be in the form of participants generating questions or problems even based on the material that's being provided. I hope this aspect is also something that is noted. And in fact, when you see the course page, you see that there are several problem sets that have been also posted, and these are the typical problems that we ask students to work on. These are problems which Professor Gaitonde has put together over a large number of years. And what you'll realize is that each of these problems in some sense is different, in the sense that there is no repetition or hardly any, if at all. And each problem requires some analysis. It's not like only, take some formula and, plug your numbers in the formula and obtain the quantity of interest. So in fact, here is where I will request Professor Gaitonde to speak a few words on the problem sets, if he doesn't mind.
Regarding the problem set, the problem set is modified by me, but I have inherited it right from my, some problems actually go back to my student days. They have been modified over the years. The total number of problems, I think, is around 100, not more than that. But it's not an exhaustive set in the sense all sorts of situations are not included there. But what is included are distinct situations which each problem will require you to start from the basic equations, but algebraically at least proceed in different ways. So you will have a combination of an adiabatic process with an isobaric process, then maybe an adiabatic process with a essentially constant volume. At least the initial and final volume will be the same. A process which is quasi-static compared with a process with a non-quasi-static, and so on. In fact, as teachers, one of our jobs is to come up with at least a few new problems every few months. And thermodynamics provides that because you have simple set of equations, but each equation has a number of distinct terms. If you say the first law is Q equals delta E plus W, you have delta E in different components, the thermal energy, delta U, then kinetic energy difference, delta EK, potential energy difference, delta EP. We generally don't include electric and magnetic systems, but if the teacher and students are comfortable, even a question on a battery or a capacitor can be included. Then it comes to the work interaction, that is Q equals delta E plus W, the W part. Now we can have a work interaction not only of the PDV kind, but tau d theta kind. In tau d theta kind, again, we can have something like a stirrer, which would be a one-way mode of work, and something you could consider something like a spring in the system, which will be able to store some sort of an energy. So that will be a tau d theta type of work, but that will be a 2D mode of work. Okay. Then you can add surface tension work, you can add electrical work. There are no really physical limits. Tomorrow we may find out some additional modes of work. But remember, the first law is just one equation, Q equals delta E plus W. So you can solve it just for one unknown. So you'll have to rephrase the problem in such a way, or phrase the problem in such a way that the student is able to either evaluate or get rid of, by appropriate assumptions, all the other terms, keeping just one unknown. Once you do that, the rest is mathematics. You have one equation, one unknown, somehow you will solve it. Try doing this, and you will find that your thought process will improve the moment you start setting up problems. And for mechanical engineers, the thermodynamic problem situations are there all around us. All sorts of machines, heaters, coolers, refrigerators, even our mobile phone. And you just look around your home, in the kitchen you will find enough illustrations. Thank you.
Yeah, thanks, Professor Gaitonde. So anyway, we can continue with our formal objective of this session. And if there are any comments, questions, or even suggestions on the remaining part of this second law discussion that I pointed out, starting with Carnot Theorem, Carnot cycle, establishing the thermodynamic temperature scale, Clausius inequality, and entropy, we can do that. Sanjay, what exactly do you wish the discussion to be on? Can you please unmute yourself and explain? Thank you.
Hello, sir. Good morning.
Yeah, morning. Go ahead.
Okay. What I mean by that is, sir, first thing, in online mode, what tools or what softwares you use or you have used or would recommend?
So I mentioned that in my response. For
Mhm.
this course, we have not used any software tool. Okay,
Uh,
and the reason is that if you look at the topics that
Mhm.
have been included in this course,
Mhm.
it's an analysis, fundamental analysis course,
Yes, yes, agreed, sir.
wherein we don't really need any software tool per se. What you can do, of course,
Mhm.
is in addition to the standard discussions that we have been having,
Mhm.
you could keep posting real life, engineering drawings or pictures
Mhm.
of equipment
Mhm.
which gets designed on the basis of these principles that we are
Yes,
introducing.
yes, yes.
So that's something that really helps the students, and it keeps that so-called interest
Mhm.
alive
Mhm.
throughout the course. But
Yes,
other than that, as far as pedagogy aspect is concerned,
yes.
we haven't really, at least I haven't really used any software tool per se. Uh,
Mhm.
Also, there is no consensus on how in this online mode one should teach a class, whether doing it
Mhm.
in a flipped mode is
Mhm.
advantageous, or whether
Mhm.
doing live lecturing is advantageous.
Mhm. Yes, sir.
What I found that when I have run it only in the flip mode, okay, last
Okay.
semester.
Mhm.
What I found that students, when they show up for the interaction sessions, then
Mhm.
uh, they have obviously assumed to have seen these lectures
Mhm. Yes,
and
yes.
taken their own notes and thought
Of
about
course.
things and so on. So the
Yes.
interaction sessions become extremely focused
Yes.
on their questions and trying to address those
Yes. Yes.
questions and issues.
Yes.
And those students then who are doing this seriously end up
Mhm.
learning this matter phenomenally well. This is
Yes.
what
Yes.
my experience has been. Of
Yes.
course, somehow you have to impress upon the students that it's up to them to really carefully view the videos. While
Mhm.
viewing the videos, take appropriate notes,
Mhm.
make sure that they have their questions noted down
Yes.
while
Yes.
and so on. But
Yes.
if someone does that from a
Mhm.
student's point of view, what
Yes.
we have found is their eventual learning, and obviously therefore the performance in the course becomes
Mhm.
very, very impressive overall.
Mhm.
So
Mhm.
that is what my take on this is. Let me before we take Dr. Vanjara's question or comment, let
Mhm.
me ask Professor Bhandarkar to also comment on this, because he may have some other opinion on that.
Just want to add a bit here.
Yeah.
Uh, huh. Just because what happens in this already prepared video lectures uh, is like a one-way talk, and
Correct.
in
Correct.
is
That's the
uh,
reason I want Professor Bhandarkar to comment, because
what happens is because in live class you can adjust your tone, you can adjust your pace,
yes,
and you get the
yes,
live feedback from the students, and by just by watching their faces, are they convinced or not? That also through visuals also we get non-verbal communication, also we get some inputs from them, and we can adjust our way of teaching, and lot of flexible we do things we can do there. But
yeah,
and in particularly this thermodynamics is so important, and such a critical subject, that from the understanding point of view, uh, it requires like it can be only, my thought is that it can be only properly taught in a live class, by face to face talk. uh,
yeah. I mean, it's a matter of opinion, in the
uh,
sense that what you say is obviously right.
hmm,
But uh, if one designs the discussion sessions in the flipped mode in a
hmm,
proper manner, there can be a good success as well. And at least
yes.
here in IIT Bombay, when I ran it last semester in a flip mode,
Hmm,
I would say that it was a reasonable success. I will say that at least 25% of the class
hmm,
really ended up learning a lot, because they were actually putting all their effort. But let
yes.
me let me request here Professor Bhandarkar to also comment, because he has been in the last 2 semesters
Okay, okay.
teaching
Yes.
in a live manner, right? So let
Okay.
me bring.
Just one point. Just not about just thermodynamics, but for any other subject like fluid mechanics. It may be for strength, heat transfer, or refrigeration, air conditioning. Yes. Like, how do you think is it a better way to deliver through online mode, or no. That's my point. Mandarkar sir, please go ahead. I will stop my this thing.
Okay. My question is, when you say online mode, you mean this flipped mode, or teaching using one of the online forums
Yes,
like Google Meet, just like what we are using now, or Zoom or
yes,
something?
yes. Direct live online class.
Acha, live online class.
Yes,
So let me first start with what Professor Puranik had mentioned. I have run this course exactly once in the flip mode, but that was to a very small minor class with hardly 9 students in it. And even there, let's say around 40% people, that means four or so, were really interested. And in many ways, you can see that these videos, this so-called EDX mode of videos, where none of the videos is over 15 minutes, so that your
yes,
attention span is, hopefully it
hmm.
is within your attention span. Of
Yes, yes,
course, I think modern kids have even shorter attention spans. So
yes,
that is the mode in which EDX had designed that their videos should be, and we are
yes,
of course
yes.
translating it exactly same into IIT Bombay X and even
Hmm.
the government SWAYAM platform. Whereas the earlier NPTEL videos, if you realize, they were whole classes, okay, and
Yes, yes,
it becomes slightly tougher to maintain the attention span for a
yes,
1 hour period, not just on a video, but in a live classroom also. The problem, of course, is the interest of the students, and as Professor Puranik said, it's hardly, see, 40% is in a class of 9, and 25 maybe in a class of I don't know how much. But if you have large classes, I can tell you it's barely 10 to 15% who are really interested. They definitely benefit. And the question then we need to ask is, who's our audience really? If it's the
yes, yes,
entire class, somewhere I feel at least our ecosystem is not such that everyone seems to be keen to study. They just have come in, and if we
yes,
want to address everyone's issues, sometimes it becomes very tough to say that the flipped mode is the best. Whereas definitely it's the best mode for people who are really keen. And I can tell you, even this EDX and all these online platforms are really good for people who come from the perspective of I want to learn,
yes, yes,
rather than just come into the classroom because they have been
yes.
told to attend the class. So that's, I think, that is where I would stop regarding talking about flipped mode and this, because it's all about our students perspective of how they should learn. Regarding online mode, well, we there's nothing that we can do right now. I teach live classes. I use Google Meet for my classes, and I use I share the screen, and I continuously I use a Blackboard, in the sense I have
Hmm.
this external software, okay, available with my Ubuntu, and I have a writing pad. Okay,
Hmm.
so
Hmm.
a Wacom pad, it's one of those normal Wacom pads where you
Yes,
can start writing. And the students who are interested, they keep asking questions, and then it becomes like a very normal live classroom, in the sense that I am teaching something, they make me deviate, then they say, why don't this I didn't understand, so I draw another thing, and you can see that and then I post the PDF on the there is a class Moodle page. So the video is recorded, and of course, a lot of students prefer to see the video because they don't want to get fixed to the lectures. But then and that is a compulsion that IIT has, that the videos have to be recorded and put up. So many students do look at the video, but and there is another advantage in the video, which I realized later, that you can play the video at double the speed. Okay, and people seem to think that gives them all the material in half the time. So, which probably is okay. And the thing is, the PDF that I put up, you realize that it's not a very organized one, because students have made me deviate from wherever I was teaching, and which is good. I at least like that. And once in a while, I'm always looking at the right hand side, see who the participants are. Just like here, I can see who the participants are, and immediately I draw something, and immediately pick someone in an alphabetical manner and ask, okay, what does this mean, or why do you think I'm doing this step? And then if that person doesn't answer, I just go down. But then, I do put people on the spot for some time at least. And some of them seem to be reasonably at least engaged. They know what I'm talking about. Some people are reasonably honest and say, sir, I'm not paying attention. So which is fine at least. But I make the effort to involve them, because there's nothing else we can do in this time where they are not in front of us, but you need to get them engaged. So that's all I can say. You have to ensure that you are continuously writing something, talking, modulating your voice, forcing it in some places, and then asking students in between just to see that their attention is caught. That is the only tool right now I know. If there is something better, I would really like to know. Yeah, thank you.
Sir,
Yeah,
just
please.
will you, after this course, will you provide some sample the tools that you know or that you use for effective online teaching? Like you said, for the writing, you are using a writing pad. Uh,
Correct.
Such tools, if you make it available, the list or references, if you provide, that will be better for us.
Yeah, the writing pad is a hardware and the Exornal
Yes.
is the software. So I will
Uh,
just say, yeah, share it on.
if you share the list of such
Sure,
tools,
sure, sure. Yeah.
please. Yes, I just want to know about the what software or what tool that Gaitonde sir has used for the entire video session of this EDX.
Okay, so that tool is actually we were writing on paper. Okay,
Hmm.
and that gets captured. Plus, there is a separate camera also on top. This, if I think, Professor Gaitonde, you or even one of the staff here, like Sushant or someone, can
Yeah.
comment on this.
See, the tools which we use, there are no specific type of tools. A simple tool which, you have a paper in front of you and a camera above you, that itself will do. If you want something more jazzy, you can use a tablet or something, a touch sensitive, like our mobile screen. In mobile screen, you have those drawing and sketching applications, so something similar to that you can use. In fact, recently I have got a small tablet like this, and there are it has its own pen, and I can sketch and I can write anything. I had just a few minutes ago tried to see whether a Jamboard can work. Now let me see whether I can make it work.
Yeah, it definitely works because I have used it heavily with Jamboard. So,
For example, now I'm opening a whiteboard. I'm starting a new whiteboard. Can you see the whiteboard? I'm not sure.
yeah, you have just shared it, so we need to click on the link.
You have to share.
No, he has shared it in the chat, so you just have to click on the link. It will show it comes up as a separate window.
Yes, sir, it is visible, sir, now.
Okay, so let's see. I'm writing something. Is it seen?
Yes, you have written ME209X. Yeah.
So this is a very simple thing. Needs getting used to, because the feel is not the same thing as as that of a pen or pencil on paper.
So Sanjay, I have used and I am using for the current semester a similar thing, only with an iPad.
See, the
So
good part I will tell about this Jamboard is that because he has shared it, I can also write on this.
Yeah.
See, this is me.
Yeah, so one can actually almost recreate the classroom, the usual classroom, with a tool like this. Is I think what the point is.
How are you writing this, Upendra?
Same, exactly the same. You have the writing tablet and the pen.
Okay, good. So it shows that you are more used to it. I'm new to it.
Yeah. I've been now using it. This is my second semester I'm using it. So
It's called the Jamboard, and the tablet is, I think, called Wacom. Maybe Professor Bhandarkar, you can mention it in on the course page or something.
So the Jamboard is part of the Google Meet thing. You can see immediately when you look at your Google Meet on the right side, it says open a Jamboard, okay, and that is what Professor Gaitonde has opened. So you can, and once you have opened a Jamboard, you can share it with everyone, just like right now he has done so. And of course, the advantage with the Jamboard is if everyone is allowed to write. Whereas what I use is a regular screen which I share, and then I use the same tablet to write on the screen. So I'll write down. I think Professor Gaitonde also brought a Wacom tablet. Is that right?
Yes.
Wacom is by far the best company in this. So let me write it here. Wacom tablet, and they come in various sizes, by the way. So yeah.
Okay, let's get back to it. Otherwise, we'll get carried away by this.
Yes. Yeah. Sure.
Yeah, I think Dr. Vanjara had for some time raised hand. So in case he has something to say, he can please go ahead.
Yes, sir. I would like to go back to the course literatures from lecture 26 of Carnot cycle to 27 Clausius inequality, and then we have moved to entropy. One thing which I am finding is that because I am having chemical engineering background, so I use a book named Smith and Oneness, that is Introduction to Chemical Engineering Thermodynamics. There is a term name like Clausius inequality is not used. No doubt, dq by t cyclic reversible always less than or equal to 0. That is in a way included over there, but in the different fashion they introduce entropy, that is directly from the Carnot cycle. We are having q by q1 by q2 equals to t1 by t2, and then we move to q by t, and that we introduce as an entropy. So my thinking over there here is it something like we can directly go, or we must introduce Clausius inequality to make it more comfortable for the students?
I think the way I understood your description is really introduction of Clausius inequality itself looks like. That's the way at least I seem to follow what you were saying from the Smith and Oneness book. But let me request Professor Gaitonde here, because he can comment the most meaningfully, I suppose.
I saw Smith and Oneness long ago, but many books, not just those in chemical engineering, they short circuit this in a small section or a small chapter. So all that Smith and Oneness may have done is skip over the intermediate steps and come to the entropy. Here we have kept everything in the open, and that is why all those nuances of details are presented. It is for you to, once you appreciate this, it is for you to decide how much detail to provide to which students, which class, and all that.
Okay. So in this regard, sir, I want to say that is it something like brand specific, or these are like basic, so can be taught in the way which you taught? I found it that students will have a way to understand it in a better manner, because that is where we directly move to entropy from Carnot cycle.
Yeah, see, we start with Kelvin, Planck, and move all this thing, and finally come to the concept of entropy.
Yes, sir.
Okay. The way we have done it, we have taken a very scenic, detailed, long-winded route. It takes time. In an actual classroom situation, you have to decide how much time you have, at what speed you can go, so that the students will appreciate, and then decide. For good students, see, you may not get more than 2.5 or 3 lectures to start with the second law and come to entropy. Now, if such a restriction is there, then obviously you cannot go or use the details, all the details in this long-winded stuff. So considering the background of the students and the applications they are going to have for their thermodynamics, you decide what is the short route you are going to use. Of course, there will be a few students who will say, "Sir, you have skipped this. I want more detail on this."
Yeah.
For those students, you can provide a reference to these videos.
Okay.
Yeah, I think that's precisely what I was going to just suggest.
Yeah.
That you can decide based on these videos how much material you can actually discuss in class.
Yes.
And obviously, these are all available freely for everyone. So for the interested students who will demand more details, as Professor Gaitonde said, you can
Yeah.
always provide links to specific videos in this series or the entire course itself.
Sir, another thing which I am thinking to discuss over here in this platform. Can I?
Yeah, please go ahead.
Sir, chemical, as in the initial lectures, Professor Gaitonde told that thermodynamics, basics of the thermodynamics is stuff for chemical engineers, mechanical engineers, chemists. Even we are having here biotechnology branch. We do teach them also thermodynamics. My basic question is, if I'm teaching it to these are all the basics, of course. So if I'm teaching it to different branches, uh, should I keep any different orientation for all? No doubt, basics means basics; they remain same. But anything particular difference in the orientation needed for the for branch specific orientation in the basics, which that we must emphasize those points in detail, can go in these points very quickly. If this is a blessed platform where all are available, so can I have some idea on this?
May I say something?
Yes, sir, please.
You will have to be branch specific when it comes to examples, illustrations, solved problems, and exercise sets. When it comes to chemical engineering, reacting mixtures, non-reacting mixtures. First, mixtures will have to be introduced in detail reasonably early. Then after some time, reacting mixtures, chemical equilibrium, all these things will have to be introduced.
Yes, sir.
Whereas in mechanical engineering, we introduce more of those thermomechanical things like pumps, blowers, compressors, etc., which chemical engineers need not do to that extent. We do chemical reactions and chemical equilibrium, stoichiometry, but only from our combustion point of view.
Okay.
I have not really looked at the biological aspects, but non-equilibrium states and such things will have to be considered for biological systems.
There actually, sir, bioenergetics is a branch which leads.
Yes.
Yeah, that's why what happened. They are also interested to know about entropy and this, especially second law, that this gives free energy and all these things, which leads to basics of the bioenergetics.
Agree.
Thank you.
So,
may I say something? On a lighter vein, a disadvantage of online stuff is we can't have a cup of coffee together. But I hope each one of you has something interesting in your hand. So cheers.
So today is so, sir, it is possible at home.
Okay, I'm lowering my hand.
Yeah, thanks. So, Dr. Banjara, let me just add to what Professor Gaitonde was saying
Yes,
on
sir.
this branch-specific aspect. If you notice this specific course ME209X that we are discussing and the lecture series that is available, I would say that this is really handling the real fundamentals and possibly again slightly biased toward mechanical engineering. I have noticed that in some other places, other universities, colleges, and so on, even for mechanical engineering in this first level thermodynamics course itself, they will introduce the power cycles such as the Rankine cycle and the Brayton cycle, even possibly the refrigeration cycles and so on. So depending on what the overall syllabus is for that course, I think you will have to take a call on how much detail you want to provide in class on these absolute fundamentals which we are sort of covering.
Yes.
And then as we said a few minutes earlier, remaining things can be pointed out through the videos to the interested students.
Yes.
Yeah.
So, sir,
Thanks.
I really do appreciate the entire course is very, very general and applicable to all. I have not find still bias for for the branch specific bias in this course.
Yeah, I agree. I
Yeah.
think that's how the effort has been made from Professor Gaitonde and Bhandarkar. And
Yeah, that's absolutely classic, sir.
yeah,
Thank you.
that's good. Thank you. Yeah. Sanjay, please go ahead if you have something.
Hello, sir. Good morning. Can we talk about something Carnot cycle and Carnot efficiency?
Yeah, please go ahead.
That yesterday, through Kelvin Planck statement, it is seen that no heat engine can have 100% efficiency. That's okay, convenient, agreed. Then we go on to Carnot theorem and Carnot cycle, and after setting up the this thermodynamic temperature scale, we the heat rejection to heat absorption ratio is equal to the temperature absolute temperature of the low reservoir to high reservoir. This ratio gets established, and then we bring that into Carnot efficiency of a simple form, that Carnot engine efficiency equal to 1 minus T2 by T1, or whatever term, TL by TH. Okay, we bring that equation to that efficiency of an engine is equal to Carnot efficiency equal to 1 minus TL upon TH. Then if somehow if we convert TL equal to 0, that is absolute zero temperature, so it it will lead to the 100% efficiency. Then so how can we take this? Or it will convert it again 1T heat engine, and then just because 1T heat engine is not possible as per Kelvin Planck statement, then we can never reach a temperature of 0. Is that what inference we can draw from this, or something missing is there?
Yeah, let me request Professor Bhandarkar to comment on this, if he can.
Okay. See, this is how I would look at it, and of course, Professor Gaitonde can comment. See, it is all about what kind of temperatures we achieve, and the law is made for the kind of temperature we achieve. And obviously, the analysis is clear that you go lower in temperature, and if you can so-called reach 0 Kelvin, you can get 100% efficiency. And if it states so be it. But we have never gone and tested it out there. Okay, we don't know if 0 Kelvin can be reached, but we cannot make such comments whether 0 Kelvin cannot be reached, this, that, because those I think have not been tested. Okay, so I don't want to comment on whether some temperature can be reached or not, but yes, as far as the analysis is concerned, if you go lower in temperature and tend to reach 0 Kelvin, you should touch reasonably good as 100% efficiency. And but the law itself was made by looking at our observations where you don't get temperatures like that. Okay, but maybe it is true that if you can get temperatures like that, you can go ahead and reject to that temperature and get whatever good efficiency you want. Probably Professor Gaitonde can enlighten.
Sir, may I please?
Yeah, sure.
When I'm talking about this, I'm referring to topic in Zemansky book. Shall I share that? I'm having a PDF right now. Shall I share that page just for reference?
Sure.
If I am allowed to.
Yeah, sure. I think everyone is allowed to share, I think.
Okay. I will just a minute.
Meanwhile, you start your share. Meanwhile, I'll put
Yes,
up my
please,
views.
Please, sir.
See, yesterday we had a discussion, I think something about complete and continuous, and I mentioned that, well, you can have an isothermal process expansion, but then there will be a physical limit to how far you can go on expanding. Okay?
Yes.
Similarly, one way to argue is that 0 Kelvin is like that expansion. It's sort of a physical limit. So, but when we say we have this mental set, because right from our childhood we absorb the idea of a 0, but the idea of a very large or infinite remains abstract, because you say infinity is something which is very far away. That way, 0 is also something which is very far away when you really come to physical situations like 0 Kelvin.
Mhm.
That is one way of looking at it. Another way of looking at things is, remember that the way we have studied this classical thermodynamics, there are restrictions. And I think in my videos I have made clear some basic premises that we assume that there are no relativistic effects and there are no quantum effects, right? No relativistic effect means if there are relative motion, the relative velocity is nowhere near the velocity of light. Okay. Similarly, from a general relativity point of view, accelerations and gravitational fields are small, they are not enormously large. Quantum stuff means that our energy interactions and hence location of states in state space, temperature levels, work interactions, and all those are continuous. There is no delta E and H nu or H delta F or something like that. Nothing like that. Now we are not sure. We know that as we go to lower and lower temperatures, quantum effects and related physics things become significant. So I'm not sure how robust will our classical thermodynamics be as you approach absolute zero. That is something to be thought about.
Good morning, sir.
Yeah, go ahead.
One question. Okay. So actually, this is regarding closed system. In a closed system, we just say that there is no mass interaction between the system and the surrounding, and only energy interaction is there. So if we correlate that concept with Einstein equation of equal to mc square, so there has to be some changes in the mass. It's also. Any comment on this?
Again, if you talk about E equals mc squared, I suppose that's what you talk about.
Yes,
You are
yes.
bringing in relativistic effects.
Yes.
We don't want to do that because all this thing is developed in ours is equivalent of the Newtonian mechanics, our thermodynamics.
So how we can? So actually, if I want to give explanation to the students, then how I can go in this direction?
In our current framework, there is no explanation which we can give. You emphasize the initial assumption that we are going to remain away from relativistic effects. We are going to remain away from quantum effects.
Yes, that's all really you can emphasize, and within that framework is what this this course functions really. That's correct.
Of course, thermodynamics as a complete subject need not be restricted to this. Classical thermodynamics is, and in the library there are a reasonable number of books on quantum thermodynamics and relativistic thermodynamics. Who is that famous scientist? Stephen Hawking spent the whole life applying thermodynamics and second law, etc., to black holes. But that is not our thermodynamics. That is thermodynamics of an expanded version of thermodynamics, which takes into effect relativistic effects as well as quantum effects, at least those pertaining to cosmological stuff.
So, sir, correct me if I am wrong. What I have given as a response to the student for that particular question was that if we consider the effect of mass in that equation equal to mc square in the form of in differential format, then we are basically dividing E with c square to calculate the changes in mass. So c square itself is the value of c is 3 into 10 raised to 8. So c square will become 9 into 10 raised to 16. So, and that too is in division.
Again, I would not comment on this because this is relativistic phenomena which we are not included. I don't even want to discuss it because I'm not on comfortable ground doing that. That is why in our very few lectures I have said we'll assume that there are no relativity effects and there are no quantum effects. And we will remain in that field.
Okay.
Yeah, therefore,
It is like playing a game of tennis. You have a court and you have an extended court. You can't go beyond that. What happens if you start playing beyond that? We don't know. At least the current tennis rules say that is not a
exactly.
fair
And I
game
think
of tennis.
that's all you need to really point out to the students, if you ask me. That's correct.
I think everybody is drinking coffee or having a snack. So may I ask a question?
Yeah, please.
Which
Yes, sir, please.
which I expected to be confronted with yesterday, but hasn't come up. So either that means what I have presented in the lectures has been completely absorbed, everybody agrees to it, or it has been missed in transit, lost in transit. See, the Carnot form of the first law which we used led us to define Q as an interaction distinct from W. And we said that energy interactions in thermodynamics can only be of two kinds, work and non-work, or other than work. And other than work, we said, is the Q or the heat interaction. Okay. And then we said heat interaction after definition of the energy change of a system. The final relation turns out to be Q equals delta E plus W. Then there is a statement saying this is the only relation between Q and the rest of the world, and any other relation that we know from our earlier studies must be a derivation from this. Do you all agree? Because whenever I have taught this to undergraduate students, at least the early batches where my reputation was not very well established, even on IIT campus, I have had to spend 10-15 minutes, erasing the older idea of students regarding Q. I don't want an answer just now, but think over it. And you can put your comments in the discussion group of the course. Thank you.
So let me also pose a question here, but from a objective of this workshop point of view. In this current set of lectures pertaining to second law of thermodynamics, specifically lectures 20 to 32, is there any participant who would like to point out, one or two things that they think will incorporate in their course based on this material that's been covered, which you otherwise were not doing? And of course, why would you want to do that? With a reason. Anybody else who wishes to respond to this, please go ahead.
Sir, may I please?
Yes, please go ahead. Please go ahead.
Sir, we will be able to provide these all lectures to the students also later on, which are given by available in this platform.
Yes, of course.
So what I was thinking is that some of the concepts which are actually, as Professor Gaitunde has also guided, that will not be, I can't spend more time in the classroom for the same. So what I was thinking is, in addition to the things which I explained in the class, I will keep this, because I think now onwards, after COVID-19 pandemic, this classroom modes will be in the blended mode, more or less. So we'll try to send these videos to the students also, so that it becomes like some of the things which are in addition to be told or to be given to the students, they will use these lectures also. Okay.
So, but of course, you realize that in case any of these students is interested and they
particular aspects which are not covered in the textbooks, or which are not clear in the textbooks, I can provide this literature in addition to what I explained to them.
Okay, but of course they can come back to you with more questions.
Yeah. But I think after all these discussions, we will be able to give them satisfactory answer.
Okay, very good.
Yeah.
Thank you.
I'll say something here.
Yes, sir, please.
See, I have a file, HTML file, which if you click on a standard laptop or a computer, opens in the browser It has links to all these videos in order. At the end of the course, I will upload the file as an attachment or mail it to you. You can use that file, and everything is open source, CC BY. So provided appropriate credits are mentioned, you can use it.
Okay.
Okay, and just consider this set of videos as an another book, a live book perhaps, or a moving book, moving image book type of a thing. So just the way you refer for a more detailed discussion to some old classical book, you can say refer to these videos. But you should also warn them that you should not take just one video or one topic out of context, because then you will be mixing up your different definitions with the definitions which are used here. So that is something which you have to help them explore.
Yeah, that's a very good point actually. That's something that we need to be careful about. Thank you.
Can we add these videos to our Moodle LMS as it is?
You can add those links, absolutely no harm.
Okay, thank you, sir.
And the original videos, each video in the proper good high definition is a few gigabytes, typically 2.5 gigabytes. So downloading it on your server is not going to be effective.
No, we need to give only YouTube link. And
so you just provide YouTube links, then all the load of downloading and internet service provision is all on the students.
I think it would be better if we add few questions after every short video. These can be in form of short answer or MCQ type in LMS or say Google form.
Sure. Each one of you should do that.
And this will enable us to know whether the student have seen that particular video or not.
Provide them as a resource, as supplement to this course. Then we will have a big resource bank somewhere.
Yes, thank you, sir.
Yeah, that would be very nice actually, yes. Professor Bhandarkar, do you have any questions to pose which will address any of these pedagogical issues, let's say, for this specific set of lectures?
No, not really. I mean, I don't really know what to say, but actually I would have also liked to know what people are doing in these times, how they are managing their teaching. So that would help me also to figure out what some of the aspects are in the present situation. Yeah.
Dr. Vanjara, please go ahead.
Sir, in some books, the third law of thermodynamics is also introduced along with the discussion of second law. No doubt, sir has covered it in his lecture series by, I think, giving a reference, like example of triple point of water, and then telling that S naught will be actually nothing else but delta S that we measure. But that is like in many books given by the postulates by Nernst and Planck, and they have given it as a third law of thermodynamics. In this particular course, I didn't find it. So I am actually searching for the reason for this thing.
The third law of thermodynamics is something which we don't really need in classical thermodynamics, particularly for mechanical engineer. Okay, and the various forms of third law of thermodynamics, there are maybe half a dozen or even more different statements of third law of thermodynamics, and they are so different that I wonder whether I should call them law 3.1, 3.2 or law 3, 4, 5.
Okay.
And many of those laws, or many of those statements talk about a material like a perfect crystal or some particular structure. And one of the basic premises or strengths of classical thermodynamics is that it makes, except for those quantum effects and continuum and non-relativistic effects, it makes absolutely no claim on the content or the structure of the material. Okay, so any law which talks about a certain type of material in our scheme of things cannot be a law of thermodynamics. Maybe I'm saying it too strongly and I may not do it, but that is not in our domain of discussion in this course.
Okay, okay, sir. Because I heard the word postulates in third law of thermodynamics, while as Dr. Puranik was telling to introduce some of the things from this sessions to the class. I would like to introduce those state postulates. Postulate 1, 2, which are given in the earlier lectures of the lectures, I think from first to 4, 6, etc.
Yes, that's a very good point. Actually, those postulates are highly useful in further developing the concept. That is absolutely right.
Yes, sir. Yes, sir. That's what I would like to add in my class notes.
And on a lighter note, if the basic premises, etc., are not followed, what happens is seen every day on the traffic on Indian roads.
Okay, absolutely right, sir.
And one more thing, before I keep quiet for 10-15 minutes at least, is I recommend that because we have been looking at Dr. Carnot Theorem's work again and again, at least before the, we close or soon after, look at lecture 29, which is titled More on Entropy. In particular, look at the first and third items. First item is known as Carnot Theory again, and the third item is called adiabatic reversible isentropy.
Yeah, that is
those the troika of adjectives, adiabatic, reversible, isentropic, are confusing to many people about how distinct they are and how similar they are. So I recommend that you go through that, because if you are a teacher of thermodynamics, you should be absolutely clear about the relations or non-relations between these three adjectives: adiabatic, reversible, and isentropic. Okay. So whenever you have time, please study S138 very, very properly. That is the third video in lecture 29.
Yeah, actually, let me add one more appendage to that description. Is you can actually generate some nice questions, or maybe even with some more effort problems, which will try and test the understanding of students on those three specific words that Professor Gaitonde just mentioned. So maybe perhaps you can note that part down, and whenever, as he said, you have the time to really sit down quietly and go through it, see how you can utilize those three words to generate some nice questions to test the understanding.
1 minute. This is only for Bhandarkar and Puranik. Everybody else, please switch their ears off. Hey, UVB and BPP, will you be available for about 10 minutes after 11 a.m.? I'm thinking of some post-course assignments for these folks. And I have some ideas which, if we agree, we can announce them in the afternoon today.
Sure.
Yeah.
Okay. So others can listen in now. No harm.
Sanjay Geji, you have a raised hand. Please go ahead.
My question is regarding entropy. Entropy property got defined through Clausius inequality, where the Clausius inequality is cyclic integral of del q by t less than or equal to 0, equality sign for reversible cycles and less than for irreversible cycles. And then it later on got proved that it is a property of a system because it does not depend on the process, as the cyclic integral is 0. But again, question remains: it is this property. If it is defined as a property, then why it depends for a reversible cycle to be 0 and for irreversible cycle greater than 0 for a change of entropy? We don't see such a double thing like inequality in other properties like change in volume. If we take uh, for a system undergoing a cycle, the change in volume will be directly zero, right? Irrespective of reversible or irreversible process. The same is for some other property like a pressure. But in case of entropy, it sort of seems that it depends on the type of process. For reversible, it is zero, but irreversible, it is less than zero. So why such ambiguity there?
I think there is some confusion here.
Yes.
Entropy is a property, so between two states, there is a fixed change of entropy or fixed difference of entropy. It doesn't matter whether the intervening process linking the two states is reversible, irreversible, quasi-static, or anything. It is only dq by t, which depends on the process. And the second law says that ds or delta s has to be greater than or at most equal to integral of dq by t.
Yeah.
Or ds must be greater than or at most equal to dq by t. ds, which is dq reversible by t, is a differential of a property, whereas dq by t is not a differential of a property.
Yes, sir, but still entropy, like it was defined as a ds equal to dq by t for reversible.
Yes, we have shown using the equality part of Clausius inequality, which is a Clausius inequality is nothing but a differential generalization of the Carnot theorem.
Yes,
I'm moving into mathematics, but if you can understand, that's the best, one of the neat ways of appreciating Clausius inequality.
yes, sir.
And I have been emphasizing that whenever in thermodynamics we see that less than or equal to sign, remember that that is the sign which originated in Carnot theorem.
Yes, yes.
And I have this habit in my own self-discipline of writing less than or equal to as a tower with less than, above, and equal to sign, not the standard textbookish
Yes, yes.
less
Yes.
than, equal to sign.
Yes,
And
that,
that is because we want to appreciate that equality has a special meaning in thermodynamics.
yes.
So, Sanjay, let me add to this. What has been shown through the Clausius inequality and specifically the reversible part pertaining to the equality is that don't think about anything else but the quantity dq over t, if it is computed in a reversible fashion, let us say. So that quantity dq over t reversible has been shown to be independent of path. Okay, in other words, the integral of that. And the argument therefore is that since the integral of dq over t reversible is independent of path, dq over t reversible has to be an exact differential, and then using that the entropy as a property has been defined. That's the way you can look at it.
Sir, that was my question. That because to introduce this entropy, they defined it like they related to del q by t reversible. They means that
Yeah,
term
because
del.
what has been shown through the use of Clausius inequality, the equality part, is that the quantity dq over t reversible is an exact differential.
Yes.
And that exact differential is then coined in terms of a change in the property called the entropy.
Yes.
That is what really the bottom line here is. Okay, and that's
yes.
the way the property entropy has been introduced. Let me ask Professor Bhandarkar to comment on this, because he also has a nice way of explaining this.
I think the better understanding can be got if you look at that video that Professor Gaitonde had mentioned, where he talks about reversibility, adiabatic, and isentropy. Okay, that really shows how you should try to. I mean, I can see to some extent how this kind of confusion has come about. Okay, but you should realize that entropy is a property. Okay, and after that you should just let go. It is nothing to do with what is the path taken and etc. etc. Because irrespective of the path taken, the entropy of a system is, because it's a property, it depends on the state of the system. So you should now no longer be bothered about it, and you should treat it like just like any other property. And then you look at this second law and write it as a mathematical equation, and then bring in adiabatic, isentropic, and reversibility, and then you will have a fairly different idea of how to present things to students. I think that video is the critical video that I think you should look at.
Yes, sir. Then related to entropy, I would like to extend. So in finding out the entropy change for any process, irreversible or reversible, yes, it is the procedure is given that we have to replace that actual process by a convenient reversible process, and then carry out the calculation and find out the change in entropy, because it is going to be the same whether reversible or irreversible. Then what is the criteria, how to select the convenient reversible process? Because it can be, it has to be quasi-static process, so it may be isothermal, maybe constant volume process, maybe isobaric process, or how, because between the two end states, when two final states are fixed, that only unique process can go through, no? That
You're right. You can make any process. You can think of any process as reversible as long as you have made it into a reversible process. So there's
yes, but
no problem in whether it is isobaric, isothermal, doesn't matter. You can, as long as it's reversible, you can be happy with it. That's all that matters.
but how to exactly select or that convenient process?
How to exactly? Okay, I think here only Professor Gaitonde. I don't know how to explain this point now.
Is there any criteria for this type of a system? You have to, this is a proper or suitable process to select.
No, I don't think
No,
so.
there
I
is
really
no.
don't think so.
Yeah, there is no such thing. Every process you can come up with it being reversible. There is no problem in this.
So what has been also shown is that for a simple compressible system that we normally deal with in our typical applications, you can then work out the change in the entropy using a convenient reversible path, and that's been worked out. So this is just an example, but as long as you are able to identify any reversible path, that your specific system that you can think about, it should not be a problem.
Yeah, and see, I don't know. See, the people always seem to have this confusion about what you can theoretically assume as reversible. You can assume anything as reversible as long as you have only PDV kind of work in a simple compressible substance, and all heat transfers are taking place across really negligible delta T's. Okay, and there is basically no dissipative effects at all, and it is a reversible process. And you can imagine most processes, at least hypothetically, to be reversible, and go ahead and do your calculation. So the simplest way I would say is, if you want to calculate entropy, especially for gases and ideal gases or anything else, especially for ideal gases, you can use the property relations. Okay, so the TDS relations. It is very easy to, because that relation will always hold true for a simple compressible substance. Just go ahead and use that, and you will get your, because it's only relationships between properties. So you can immediately calculate any property that you want as long as you know how the integral of the other properties are going about. So I think that is the best way to do many things.
Yeah, so Sanjay, let me point out again that because S2 minus S1 is defined as integral going from state 1 to state 2 of this quantity dq over t in a reversible process. You can then essentially bring in the first law to replace that dq by stipulating that the process that your system is undergoing is reversible, and then because we deal mostly with simple compressible systems, as Professor Bhandarkar just mentioned, the most convenient and common work in a way that we deal with is this PDV work, And as long as you claim that that PDV work is going to be reversible, which means that you are throwing out any dissipative effects, and also it is going to be a quasi-static situation. And then that's it. That's all that you really need in order to go further. And once you specify the working substance to be something more specific like an ideal gas, then you can bring in those property relations corresponding to the ideal gas to actually work out the integral.
Sir, with some example, let us take one system of a rigid tank containing some gas, and it is being churned with the help of a stirrer. So to find out the entropy change, which is for this irreversible process, it may be constant volume. It can be assumed to be a constant volume, or it can be assumed to be a constant pressure process.
So what do you think?
Both
Let us
are
say
possible.
that I have a rigid tank, and it is filled with some, let's say,
Gas.
for the sake of our discussion, ideal gas, let us say. And let's say initially it is at certain conditions, right? Let's say it is at pressure P1, volume of course fixed here, and temperature T1. And then, as you said, you have this stirrer work. So you have introduced some mechanical stirrer, let us say. And you are going to start stirring from some time, and the stirring will happen for a certain amount of period and so on. And based on that stirring parameters, let us say that you are in a position to compute that stirrer work. Okay. So now, how would you go about finding the change in the entropy that has happened over this process? That's the question, isn't it? Yeah. So what is your thought process?
Yes, since volume is fixed, or since the tank is rigid, probably I will start with the constant volume process, assuming it to be. And
not probably. It is a constant volume process indeed. That is correct. Yes.
But let us say that the stirring action is not disturbing the pressure, so it can be constant pressure process also.
No. So now you need to think about it from the first law point of view.
Yes,
What
okay.
would first you employ, let us say, the first law statement for this specific system. Okay. And if you write the first law now here, what would you write? You would write it as Q, the heat interaction that has happened in this process, equal to delta E plus W as a general form, right?
Yes.
Now you need to bring in more assumptions in order to be able to work out the details.
Yes.
So let us say what may be an assumption that you want to bring in absence of any further information that has been provided as far as the heat interaction is concerned.
Yes.
So I would say that if nothing is specified on the heat interaction, we can assume the process to be adiabatic.
Yes.
So
that's one possibility.
Yes, indeed. But if there is a heat interaction happening, then you also need to provide that detail somehow in this situation, so that it can be computed. Okay, so let us say that it is adiabatic. So Q may be Q will be equal to set to 0. As far as the change in the energy is concerned, delta E, you can very well argue that as far as the kinetic energy and the potential energy terms are concerned, they are identically equal.
Negligible.
Negligible or identically 0 if you wish. So what is left is only the
internal energy,
change in the thermal energy.
Internal energy.
Yes. And that, because it's an ideal gas, can be expressed in terms of the specific heat.
Specific heats, yes.
At constant. Now here you'll have to bring in a constant volume times the whatever the mass that we have in the
mass,
tank for the gas,
MCV dt.
And times the change in the temperature, and that better be equal to the stirrer work that is going in, isn't it? So this is the first step that you have to actually execute here. If you pose this problem to the students that I want to find out the change in the entropy, the first order of business here will turn out to be change in the temperature that you can compute based on the first law statement. Now, you can always compute the change in the pressure that is going to happen based on this change in the temperature. Correct?
Okay.
Because it's a constant volume process, and you have a certain amount of energy through that stirrer work into this system. So the pressure is going to change. In fact, it's going to
change.
increase. You will actually show that the pressure is going to increase here. And you can bring in the equation of state for the ideal gas to actually compute that change in the pressure. And then once you have the change in the temperature and the change in the pressure, assuming that you knew the initial conditions in terms of temperature and pressure, you can utilize one of the developed expressions for the change in the entropy and complete the analysis. So this is a nice example wherein you will have to bring in everything that you are you have
Yes.
learned so far.
Yes.
Yeah. So Professor Bhandarkar, do you want to add to this, please?
So constant pressure is no longer valid here.
It cannot be, right? If it's a constant volume system, and if you are putting in certain amount of energy through the stirrer,
Yes.
the pressure cannot be remaining a constant.
So okay. So only option is
So
to have a constant volume.
Yes. Well, that's because of the setting of the problem is such that you are dealing with a rigid tank with a certain amount of gas inside the tank, isn't it? So
Yes,
because the tank is rigid, there is no scope for volume change, and that's the reason this is a constant volume process.
Okay.
So one thing that I would like to point out, since you brought this example up, is that oftentimes when we have actual problems of analysis of systems wherein the second law of thermodynamics is brought in to compute the change of entropy and so on, you will realize that it almost always involves the first step as your first law calculation. Okay, so most of the problems that you will actually generate for second law analysis will end up having by default the first law analysis built into this situation.
Yes, sir.
Okay, so either Professor Bhandarkar or Gaitonde can add to whatever I was talking about, or anything else.
Yeah, I think it was described. Okay, I think Sanjay, all you need to realize is that your initial states and final states have to be the same, have to be whatever were in your original problem. So, as Professor Puranik said, you had a constant volume system, so your initial and final volumes were same. Then you use the first law. You found out you wrote delta U is Q minus W. Q was 0 in this case, and W was not 0. So you found delta U. Now you use the ideal gas law. You figure out that P has changed. So you know that both P and T have changed. Now it's up to you. I can take a very simple approach. In fact, that is what I would do. I would just use the TDS relations, because I will just write what the TDS relation is for this case, and it would be just du is TDS minus PdV, okay, or TDS is so, and then I will say, okay, in this case PdV is 0 because dV is 0, so I will just integrate ds is du upon T and get whatever I want, and it's immediate because I know what the endpoints for U are. I will get what the endpoints for S are, and it's entirely a property relation. Okay, everything involved here is a property. I can immediately integrate it and get what I want. So that is all that I need to finish the problem.
Okay.
So just for an interesting variation of this problem, instead of the stirrer work that you talked about, you could even have an electrical resistor, let us say.
Yes.
And then you can provide an electrical work input to this gas of, let's say, the same magnitude that you were talking about for the stirrer work. And you can redo this in the same manner as was. So these are the kinds of situations that you can, of course, generate to test the understanding of these ideas and concepts.
Yes.
Yeah. Anyway, thanks. I think Dr. Vanjara has a raised hand, so please.
Sir, the most common thermodynamic term from my point of view, even to a layman, is like entropy. And it is if we go to the significance of the entropy as like measurement of the randomness. And a very interesting thing which Professor Gaitonde has told in one of his lecture is that we are introducing in first law as well as in second law, not the absolute entropies, but absolute properties, Rather, in second law, we are introducing change of entropy, and in first law, we are introducing the change of energy. So, is it worth to discuss the significances of this delta S, delta E, or even absolute S, absolute energy, everything in the class to make it more worth discussing in the class? Like delta S is degree of irreversibleness of a process and something like that.
Let
No,
me
let
request
me.
Professor Bhandarkar. Yeah.
Yeah, so I don't think, see, there is no, you can always tell that absolute so-called value of energy and entropy have no meaning for engineering calculations. Okay, we never use them. We only use delta E or delta U and delta S to get what we want. Now, it is not okay to talk about some randomness business here, because that only adds to the confusion. What you can use the second law and change in entropy is just to decide whether a process is possible or not. In fact, for us, that is the only significance, that the entropy is a property which will tell you whether the process was possible or not. And if that you can convey to the class, that would be the job done. In fact, in chemical engineering reactions, etc., they all bring in, Gibbs free energy, increases, decreases, everything. Finally, you realize that the derivation is the second law only.
Yes.
Okay. So it is all about whether a process is possible or not. That is what this will tell you. And don't tell just because the entropy has increased that something has irreversibility has increased. That is absolutely not true. Okay. A system can have its entropy increased in a perfectly reversible process, and you should not confuse reversibility with increase in entropy of a system. So that should be extremely clear.
Yeah, that lecture number 29 again, I will point out here, where those three words have been very, very carefully explained. Irreversibility, adiabatic, and
Yeah, similarly,
asset
another question that people keep asking is, oh, this system entropy decrease, how is that possible? I mean, there is no law against that. Any system entropy can increase or decrease in a reversible process. It does not matter at all. It all depends on what is happening along with that process. Okay, so a reversible process means this so-called entropy production term we put to zero, but everything else, there can be heat transfer, there can be work transfer, there can be change in U, there can be change in S, and the change can be plus or minus. It doesn't matter at all. Okay, so please keep this in mind.
Yeah, that's the reason. Again, I will emphasize that lecture number 29, as what Professor Gaitonde mentioned earlier, that's probably one of the most key elements of this topic. So please go through that once.
Yeah, means we should keep it confined to the feasibility aspects of the
Yes, correct. I think that's a very nice way of putting it. Yeah.
Okay, thank you.
Yeah, Girish Undale, I think yes, these recorded sessions are going to be shared. The core staff can comment on that. And I think graded activity 5 is also explained. It's essentially, again, generating one question or a problem, as has always been the case in this workshop, based on the topics that have been covered for that specific session. That's about it. Yeah, in fact, that's one point again I would like to emphasize. If you go through that lecture 29 and the description and the explanations related to those three terminologies, I think there is a lot of scope based on that to generate good question or even problem through some effort, which will test the understanding of this of the students on this subject. Or I mean, this topic rather. Yeah, Ms. Madhu, I'll just mention that I'll inform the core staff to take care of that. Yeah, Dr. Anandan, we will be doing that, the extension of deadline for the submitting activities. And after this session, I will discuss that aspect with the core staff. And in the afternoon session at 2 p.m. When we begin, the last one for the interaction, I'll announce the new extended deadline. That's something that we have already noted, and we will announce that in the afternoon session.
Yeah, any more comments? I mean, I think the next set in the afternoon is probably 11. I think that's open systems, correct? So before that, anything else on the current
Hello,
set
sir.
of chapters?
Hello, sir.
Yeah, please go ahead.
Sir, we are having one subject of heat transfer in both branches, mechanical engineering as well as in chemical engineering.
Mhm.
Is there a way to, very good, excellent way for the students to connect them with this basics of thermodynamics?
Now, you mean what?
Yeah,
Some kind of book? Some kind
no,
of
no,
book?
no, sir. Like I'm starting course of heat transfer.
Okay.
Then I would like to connect it with second law of thermodynamics. Then
Okay.
can we start from like entropy change of heat reservoirs? I think that is also discussed in one of the lectures. Changes
Correct.
of,
So, but okay, the question is when you're teaching heat transfer, what aspects of entropy generation would you like to bring in?
yeah, yeah.
No, what is it that you would like to? What is the motivation here, and what is it that you would like to convey?
Sir, it is like heat transfers from higher temperature to lower temperature, which actually a general observation. But although in this particular course we have not taken those things into consideration, like higher temperature, lower temperature, we have introduced it later. But
Mhm.
uh, I'm actually searching for the ways, because generally in most of the courses, most of the syllabus, the heat transfer course comes later on. So
Yeah, correct.
so what happened? There are actually many a times the connection is with second law. Can we make it interesting in a way in the classroom to in heat transfer that these two subjects are related in a way of delivering them in the class? That's what my concern is.
I'm not sure. So, what? See, maybe you want to connect which part? Is it the part about entropy generation? Is it part about
No,
energy
sir.
balance? See, for example, if you
Regarding
are teaching heat transfer, okay,
yes,
if we blandly start teaching about conduction, convection, radiation
yes,
without
sir.
initially involving some kind of an application, and the most useful application for at least for engineers, both mechanical as well as chemical, is a heat exchanger. I mean,
Yes,
heat
yes.
exchangers are ubiquitous in any industry, power industry,
That's what we
chemical
do
industries.
conventionally, sir. Yeah.
Correct. So there, you can, if you want to show the entropy changes in both the streams, let's say there is a hot stream and a cold stream, you
Yes.
want to show the entropy changes and then say, see, because there is such a big delta T, this extra, there is an entropy generation term already being involved here. If you can show that, I mean, that is something you may want to do.
Yes. Yes.
For us, we a lot of times we talk in engineering applications when we are talking about Rankine cycles, Brayton cycles, Otto engine cycles. So all of these places we definitely do connect the connect it to the Carnot cycle, connect what can be the maximum efficiency, why the efficiency is not maximum, which are the heat reservoirs technically, where is the heat coming from, where is the heat going to.
Yeah. Yeah.
Those things can definitely be shown in any
Okay. Okay.
put in any course. So those are the things that we would connect to. That's what
Yeah.
I would say. Yeah.
Okay. Okay.
So in I mean, if no one is talking, I think definitely we want to. Yeah, I think Professor Mathur has written that thing. ds is dq by t plus dsp. dq refer to actual heat transfer. Yes, that is true. It refers to the actual heat transfer in the situation. That's true. So that is the key statement. If in a process the entropy doesn't change, then ds would be zero, and it is called an isentropic process. Okay, that does not mean that it is going to be a reversible process. That should be kept in mind. If dq is zero in a process, then it's called an adiabatic process, and if dsp is zero in a process, then it's called a reversible process. So those are the three things that you must keep in mind, and then you realize the equation is such that if any two of the quantity, and then dsp is either zero or positive, that is the restriction that second law places on it. So this is the key equation that we would normally use to analyze many things. Okay, and the other point of understanding that you must have is any one of them can always be zero. So you can have either an isentropic process or an adiabatic process or a reversible process. But you realize that if you put any two of them zero, then automatically the third becomes zero. Okay, so an adiabatic reversible process will necessarily be isentropic, and an isentropic adiabatic process will necessarily be reversible. A reversible adiabatic process would necessarily be isentropic, and so on. Okay, so if you realize many of our cycle analysis that we do in thermodynamics, okay, many places, everywhere we in the standard analysis we assume reversible processes, and if whenever those processes turn out to be adiabatic, automatically they are isentropic by this condition. So that is how we end up doing most of our analysis when we do cycle analysis. That's all that I would like to point out. Anything else?
So let me quickly add to what you were saying. One can always generate some situations where the process will be isentropic, and therefore the left hand side of that equation, which Professor Mathur has written, is zero. But then there can be a heat transfer, and one could then pose a question to heat interaction. One could then pose a question to the students that if we have such a situation that the process is isentropic, but there is a heat interaction involved, then that heat interaction, as far as the system is concerned, has to be of one type only. And what can that be? Such questions can generate and understand the test the understanding rather of the students on this aspect. There is a raised hand from Deepen Banoria, so please go ahead. We have only a few minutes to wrap up.
Sir, I have a small concept regarding the entropy. As yesterday I have asked the question, and I want to say that whenever we taught entropy to the entropic concept to the students, they will ask usually if the entropy is related to something that at a molecular level, then how can we relate that with some elastic property, or you can say entropic elasticity concept? How can we make them understand?
Well, actually, to be honest with you, I have never heard of these terms. So I don't think I am going to be in a position to answer.
Okay.
So I would say that, at least at this point, there is no point in trying to discuss that. See, you're going to the microscopic scale on this kind of a discussion. Okay, and
Yes.
we should, at least when we are talking of this course, we just stick to the macroscopic level. We say, let us not get into this, because it just adds to the confusion. The microscopic set of things can be done separately. So as I said, all the confusion regarding thermodynamics is basically because someone wants to bring in an applique or some kind of an explanation which they think will make the matter easy, but it doesn't do it, unfortunately. All those explanations have actually confused the matter. Whenever we talk about atoms and molecules and randomness, then that's all people seem to be talking about. They don't get that all that we are really doing is figuring out whether a process is possible or not. And that should be the key thing to be emphasized rather than this, because when you come to molecular level, finally it will always be the same thing, whether something is possible or not. Okay,
Yes, sir.
so that is the only thing that needs to be. Otherwise, if we start saying, no, this is how you relate entropy here to entropy here, and then people will start thinking about it and not pay attention to the main thing on why, and then people keep asking, what is the use of entropy? That you realize that the use for it. Okay, whenever we do a cycle analysis, we know exactly, we'll tell you this process is simply not possible because you are just violating the second law of thermodynamics. But most people don't seem to realize that. So that is what needs to be emphasized. I would say that should be it.
Yeah, I think the use of this property entropy for this classical thermodynamics or macroscopic thermodynamics course, specifically, designed for engineering students, should probably be limited to the feasibility of that process. As I think it was probably Dr. Vanjara who mentioned that word. I thought that was a nice way of looking at it.
Thank you.
So of course, we have limited time, so we can discuss only so many things. But the entire set of lectures is available, and again, my request would be to go through those carefully. In the afternoon session today, we will talk about the extension to all these things to what we will call open systems. And if I remember the lecture numbers correctly, they are from 37 to 41, I think. And those lectures are, you will see, given by Professor Bhandarkar. I think it is 37 to 41. It is mentioned in the workshop
Yes, sir.
schedule.
Yes,
Yeah.
they are 37 to 41, sir.
Yeah. So there you will see how we extend the concepts and the ideas developed for closed systems so far to open systems. And of course, from mechanical engineering point of view, for sure, these open systems are very, very important, because we have been talking about, the Rankine cycle, the Brayton cycle, and so on. The individual components in those cycles, such as, say, turbines or pumps, compressors, heat exchangers, etc., they are all individually open systems where mass flow rate goes in and goes out and so on. So how in this specific course we extend the closed system formulations so far to the open systems is something that has been outlined very nicely in 37 to 41. So that's what we will take up in the afternoon session today from 2 p.m. to 4 p.m. So with that, I suppose we can wrap this session up and reconvene at 2 p.m.
Yeah, I think, goodbye. Thank you.
Yeah, thank you. So we will reconvene at 2 p.m. then.
Yeah, thank you. Thank you
Yeah,
all,
thanks a lot.
sir.